Welcome everybody to the third Minerva lecture by Wei Zhang. We of course should acknowledge again the Fernholzers for these great lectures that they support and all the activity they support around the department, which gives it a very special life with these exceptional lectures that we have quite often now. And this is no exception. And Wei will, after explaining to us local to global principles on sections of quadrics, and then higher dimensional Birchman and Dyer and Tate-Shafarevich finiteness, will now explain to us an old formula. Sounds like it's due to Siegel and Wei. It's not a joint paper, I can assure you. He'll explain it to us what the Siegel-Wei formula is and what is new that he has to say. Thank you very much.
Thank you, Peter, for the introduction. And yeah, it's a pleasure and an honor to give a talk again. So I will now again start with a quadratic form. So the classical Siegel-Wei. So now
Since I'm running this, anybody on the Zoom, we're not so full today, and you should feel to participate. Just unmute yourself and ask a question. It'd be kind of interesting to see if it works.
So we talked about local to global principle for quadrics. So let's go back to again to that question. Suppose I have a quadratic form with say integral coefficient. So now I want to consider the question where now I want to understand when or how many solutions there are. Say n by n symmetric matrix with integral coefficients. I'm interested in the quadratic equation. Say x times a times x transpose equal to so let's say an integer m. So x belongs to so we want to do counting how many solutions there are. Now we apply our this local to global principle. I mean the idea maybe. So maybe we should look at the question of solutions modulo prime powers. So let's say I want to consider let's actually give a notation. So here so let's look at the solution modulo power of prime numbers. So the local question now. We'll look at the local question. So I want to look at the same equation, but now let's consider the solution. The congruence equation, say modulo power certain power p, say p to the I power. So this will give us some, let's collect the number of solutions. So I can look at the number of solutions. Let's call it, the number of solution called, the solution is called n, depends on a and m, but also we're looking at a solution over z modulo p to the I. So let's denote all such solution. Let's collect all the solutions. Let's consider the number of solutions. So in an ideal situation, this might behave very well as a sequence of I. So it's a sequence of I. So in a special case, if I is 1, so in the case of I is 1, we're kind of counting the number of solutions in the finite field, z modulo p. So that's something we kind of looked at before. We want to know how many points in the residue field. It turns out if this equation behaves very well in the sense if it has good reduction modulo p, then eventually, essentially knowing this number will give you, in some sense, there's not much interesting information besides the cardinality on the first level. Right, so that's in the smooth case. So smooth case, this can be quantified. For example, if A has a determinant and M are both units, periodic units, so in that case, so there's not much new information besides the first piece. However, if in the more general case, in this case, so okay, z modulo p to the ith power, this is essentially the same as the first one times maybe times some sample factor, actually, some power of maybe p times some simple factor, p to the ith power times some simple factor. So in general, this might be more if it's not smooth modulo p, then we have more interesting sequence. But anyway, I can still consider the so-called density. Namely, I consider the ratio, so the number of points modulo p to the ith power divided by. So we want to compare, the number of points with a certain maybe standard space. Well, experience suggests, for example, if we have an affine space, we know the expected number of points will be p to the I to the dimension of the variety defined by that equation. So the dimension of I should have given a name maybe. This variety defined by affine equation depends on A. So the dimension, maybe the generic fiber. So we're collecting the information. We're comparing the number of points with the number of points of the affine space of the same dimension. This kind of consideration can be applied to arbitrary variety, right? You can just take any variety over Z, you do this reduction, then you make this comparison. So okay, let's call this density. So then, okay, where A representing, so the equation is about representing the integer m using the n by n symmetric matrix A. This is some kind of density, or maybe even local density, because it's for the prime p. So I should have also put a prime p maybe, so to indicate. So ideally, maybe we should have collect more information rather than just this limit. For example, I think Igusa considered, so just a side remark. So Igusa considered, this generation series. Maybe one should collect all the solution, all the sort of higher and higher congruence. But then you put you write put a generation series. So that generation series should give us more information. But here we're collecting one piece of the information. So just take this limit. Right. So then, well, maybe this sort of density measures how sort of how many solutions that locally modulo power of p And maybe you should expect that this local piece of information should tell us something about the global solution. Right? So here, so maybe let's consider all those density for all prime p. But then you say there's clearly one problem, because the local density only remember the information modular power of p. So it might be possible that for many different matrices A, they give rise to equivalent local questions, actually at all primes. Right? So we have to collect all those. I mean, our sort of local consideration will not distinguish those sort of quadratic form defined by A. So here, therefore, we should consider. Let's consider the following set lattice. So for simplicity, let me consider so rank for the given rank n. So rank n lattice is integral quadratic lattice. So lattice is with a quadratic form. Just for simplicity, I'm going to assume they have let's see, unimodular. So determinant of A is equal to 1. I'm actually also even, I can just to simplify the two-adic situation. So if you don't like that, you can work harder to figure out what happens when prime p equal to 2. Anyway, so today I'm going to kind of pretend the prime 2 doesn't exist. So we always ignore the two-adic subtlety in all these considerations. So okay, up to the obvious sort of equivalence relation. So, for example, given A there, I can produce, right? So z of nth power. Suppose I have such using A, I can define quadratic form. And we will not be able to distinguish by this consideration. So therefore, I have to, the best I can expect is to have the following, which turns out to be true. I think Siegel proved the following theorem, which is that, well, let's consider the number of solution. Let's actually introduce a theta function. So I can, given a lattice, it's called lambda here. It's a data of a free rank n Z module with a integral quadratic form. So I can introduce a theta function. So this collects, it's called theta lambda. So I can even view this as a Fourier power series where I get so Q to the norm. So I write bracket to indicate the norm defined by this quadratic form. So then, well, this is the same as in I can collect starting from integer m from 0 to infinity, where the number of solution is called n of lambda representing m, so q to the m. So naturally, we might hope, as long as I collect all those lattices together, positive, right? Yeah, thanks. Yeah, positive definite. Yeah, positive definite. So, right. So I only have a non-negative term here. So what Siegel proved is the following: is if I put everything together, well, say if I fix integer. Let me only do the case when this is non-zero. Then I can, if I collect all the number of solution, lambda inside set of positive definite of given rank. So this number, so So okay, here one has to give a weight, so give a times actually the size of the automorphism group of lambda. Since lambda is positive definite, this group is actually a finite group for every given lambda in the set. So again, so now maybe we should hope this is exactly, I mean, determined by all those local density. So O prime P, so then of M at P. So here I'm not going to write. So the A locally they give rise to the same equivalence class. All those lattices locally they give the same equivalence class over all primes. So in fact, you can also do the same for Archimedean place, where you get a bunch of spheres with radius given by maybe square root of m. So you can also put some volume factor at infinity. But I'm being kind of, let me write A. So this is not a precise. So up to right. So this is roughly what Siegel proved. So on the left-hand side, it's counting the number of points for a given integer m among all the lattices which are locally equivalent. On the right-hand side, I do have all those sort of local density for all prime p. So another way of writing this formula is to express the left-hand side while using the theta function. So another way of writing. So if I weight the theta function by the size of automorphism group, so so this will actually equal to, well, up to a constant, explicit constant. It's essentially the Eisenstein series of weight n divided by 2. So its Fourier coefficient can be sort of explicitly written down. Remember that, and let me recall you that the Fourier coefficient, mth coefficient, is more or less a constant times the divisor sum. So this is sum over divisors to the power d divides m. So which really tells us what are the, those local density can be really explicitly written down. If you factorize, and I can factorize this in terms of prime p dividing n, and for each. So I will leave you how to sort of translate from this formula. You can translate to get an explicit formula for the local density over there. Okay, so there is an easy way of generalizing everything. I can replace. Okay, maybe let me write over here. So this is kind of in the case of one equation, I can impose more equations by replacing the equation. So do the same thing. So replace the equation. So the early equation by, well, so x times a times x transpose be equal to a higher rank symmetric matrices. So T, for example, R times R. So I can do the same. You can make the same definition. So locally, you're also doing this counting. You take this limit. So this can be generalized. Then I think Siegel, or the classical Siegel VE, says you have the same. You pretty much have the same kind of equality, except instead of one equation, you have a system of quadratic equations. Generalize to this generality. Right. Okay, so that's so he did already in this generality. Could be, yeah. I didn't check his 1934 paper. Right. Okay, so right, but also more right, to even more than positive definite, or also for okay, there's also right for I said quadratic, there's also Hermitian. So there's a Hermitian version. So mainly I consider Hermitian form rather than integral quadratic form. And right, so that, I mean, yeah, okay, maybe I should also add. So here I'm now writing a most general statement. So there's also later work by Kudla-Rapoport and so on. So those will be also.
I'm just trying to understand. So what you're calling Siegel Wei, the Siegel mass formula is one thing, and the
Right, yes. So here I was only writing a statement when this is non-zero. Although here you see this equality, since I know both sides, a priori I know both are modular forms. So this is known to be modular form of a correct weight. So as long as I know the equality for the non-degenerate coefficient, then I actually get automatically equality for the constant term and so on. So where for the higher rank, it seems to be more tricky. So that, I mean, knowing the non-degenerate coefficients does not necessarily imply the equality you want. So indeed, I think there were more works involved in order to prove the full, actually, right, you generate the theta function to sort of higher genus Siegel modular form, and there is also a Eisenstein series on the right-hand side. Maybe I should write one example of this Eisenstein series. So because right, so what the the result looks like is following. So the Eisenstein series. So now you would call the Siegel Wei Eisenstein series. So it looks like, well, let's say on the Siegel upper half space, let's call it Hg. The Siegel upper half space. Looks like, suppose that tau is the variable on the Siegel upper half space. Its real part, it has real part and imaginary part. So here it looks like sum over, it's this sort of familiar formula in the case of genus 1. So C tau plus D determinant to certain weight. Then you also put a complex variable, determine absolute value to the S power, well, determine absolute value to S power, where S is a complex variable. Right, there's also imaginary part of tau to the S power. Maybe there's 2S actually, negative 2S. So where C and D has to go over to the symplectic group, CD sort of SP2 to G of Z, modulo a suitable upper triangular sort of. So yeah, so I mean it's some kind of it's an Eisenstein series which has a very explicit form. So the point is that its Fourier coefficient will look like certain normalized product of local density. All right, so that's the classical Siegel V, where we should have compared this formula with what we saw for the Born-Swan-Dyer conjecture, because remember we could have written, at least conjecturally, the BSD formulation as well for the integral curve E. So we wrote before, I have product over P, where the number of points of elliptic curve E over Z modulo P. Okay, normalized by dividing by P to the dimension, which is 1. So that's exactly this quantity we look at locally. Actually, if you compare here, it's the same. Except now I have a curve which has good reduction for almost all places. So I'm ignoring the bad places. So it's exactly this quantity here, and the analogous quantity for elliptic curve. Left-hand side, well, conjecturally, it's the number of points. The number of points. Well, it's asymptotic of points, rational points. So with height being inside a disk with radius, it's of the size of log x. Oh, I shouldn't use x again. So it's well, good. So it's right. It's a variable here. So left-hand side, it's counting number of points. Okay, up to some constant multiple here. Only the magnitude is comparable here. So in that sense, they look very much alike. Left-hand side we're counting the number of points, either the integral points of all those quadratic form within the same equivalence class. Where the elliptical curve case, we're counting the number of points within a given radius of a disk for the Laurent height, the metric given by Laurent height. Right. Okay, but of course here this formula is much more elementary because for the reason that one can even compute explicitly from this classical formula, we know what is this local density, what is the form of the local density. All right, so that is the classical Siegel V. So let me now move to what one may call arithmetic Siegel V. So let me be slightly more precise for the local density, actually, in order to state. So we have to do two things. One is for the local density. One is for the global points. So what should be replaced, and that's both sides of this equality. So let me work with a local situation. So locally, for the density. So now let me consider I have a choice to make. I can either do quadratic case or a Hermitian case. So the quadratic case is easier to state, but the results become more complicated. The Hermitian case, it takes more time because we have to always consider a quadratic extension, but then the final result looks much simpler. Okay, so I'm going to do what I think might be easier. So we do the Hermitian case. So we take quadratic extension. So I'm ramifying locally, so periodic fields. Right, so now, consider integers of f, of f0, and so on. So I look at the Hermitian space, or integral lattice, let's call it lambda. this will be a unimodular, or self-dual lattice in a certain Hermitian space, so called a V Hermitian space of dimension n. I want to consider, I want to kind of sort of rewrite what we did before in the language of lattices. So suppose I have such a lattice which is fixed, then I'll consider another lattice, L, arbitrary lattice, so integral lattice, but not necessarily self-dual. Might not be even in the same space, so in a different space. Right. So they might have different dimension. So what happens is I can consider consider the equation defined. Well, if I choose a basis, I end up with equation which we had considered before. So if I choose a basis, I can write down the well, I can look at the question of embedding, how to embedding from L to, well, suppose this has larger rank. Preserving the quadratic, the Hermitian distance, so isometry embedding. I can consider this as well. Really, this is sort of, if I choose a basis, it's going to be given by the equation I wrote before. This condition of preserving Hermitian form precisely is given by that equation, or a set of equations if L has a higher rank. Isometry. So here I can even write. Well, so what happens is here. If I vary the rank of lambda, so this turns out to be, if I consider the density, so the density will be, so let me call this representation of L lambda. So I view this as a scheme over OF. So then the density lambda L is precisely given by definition. So this is the same as the points O modular uniformizer to ith power. Then so I'm kind of rewriting the definition p to the I to the dimension. It's generic fiber dimension. So then limit I goes to infinity. So this actually is a polynomial. So fact. Now I'm going to view this as a function of lambda. So, but lambda is sort of self-dual lattice. So what only matters is the rank. So the rank of lambda is kind of the only. Once I fix L, the lattice L, the rank of lambda is the only sort of invariant. So as a function of the rank, this is actually a polynomial. The density lambda is a polynomial. Well, now it's as a Q coefficient, but polynomial of Q to the rank of lambda, what P. Well, I didn't tell you what is the residue cardinality. It's called a Q here. So Q is a number of points of the base field. Residue field of the base field. And if you normalize, I can even divide by some sort of simple factor. So I can normalize by dividing by dividing by some simple factor, I can get actually an integral coefficient. So in other words, there's a polynomial, give you this quantity when you vary the dimension of lambda, the rank of lambda. Right. So I'm gonna kind of write the same notation, although it's a normalized one. So that has a Q coefficient, maybe because of negative actually. Negative rank. Okay. Anyway, so it has a very very good property. Right. Here, this is for the p-adic place. It's right. It's so this is exactly the scheme defined by that equation, or maybe high dimension version because my L might have higher rank, but it's so the the number of points I forgot to write. Maybe that caused some confusion here. So I'm defining a higher rank version of that. That was for the rank 1 case. If L has rank 1, we embed an integral lattice of rank 1 into higher rank. It's exactly you're looking for a vector here whose norm is given. So this is a generalization of the local density I wrote before to higher rank target. So, well, the source. So if L has rank 1, it's what exactly we did before, locally, this. Right, okay, so that, I'm gonna write down one example. So one example where this, there's a formula, so one example. So in the case of rank 1, I think that you can even guess what the formula would look like using, it's essentially when we were rewriting the divisor sum function. Up to some shift of this rank. So I mean, you have to normalize correctly, but anyway, if you normalize in the right way, so I'm gonna show you what the local density polynomial looks like. So let's look at the case when L has, so here then, let's write it this way actually, because lambda is considered as a variable, so I only have to remember L. So if L has rank 3, given by the Hermitian form, given by say uniformizer pi or p, so rank 3, such a lattice. So it's dual lattice looks like uniformizer. So 1 over uniformizer times L. So in this case, this polynomial then of L, it's a polynomial. Let's call the variable x. Looks like, so I'm gonna write it. So 1 minus x, 1 plus qx. It's a degree 3. So the degree is precisely the volume of the valuation of the determinant. Then plus q squared, q cubed plus 1 times 1 minus x. Anyway, it has, if you expand, you will get actually a almost symmetric. So 1 minus q plus q squared x minus x squared plus minus x cubed. So so if you plug in, the rank q to the rank of lambda, you will get this local density. So that's what it says for this particular lattice. Right. So the degree is actually always degree has a polynomial with a variable x. This is always the variation of the determinant of lambda. So if you write down this matrix, Hermitian matrix, so and it has a function equation. You see it's almost symmetric up to a sign. So the sign is precisely given by the parity of the valuation. So in this case, the valuation is 3. So I get a cubic polynomial which has a a function equation relating the two coefficients in the. So that's what we have for the local density. So again, this is sort of one way of writing the Fourier coefficient of the Eisenstein series. But only for for the pth term for each prime p. Right. Oh, no, I said it's a fact. So it's right. So in other words, if we change lambda, it only changes in a simple way. It's interpolated by a certain polynomial, right? So the proof is not. I don't have a simple explanation. So, but it can be understood in terms of an continuation of a Fourier coefficient of the Eisenstein series. It's one way of expressing that. That fact regarding Eisenstein series. So that finished my sort of half of generalizing that part. So okay, so here then I have to tell you what I'm going to do with the left-hand side. So here I consider this set of lattices. I'm going to sort of define a geometric space which generalize the set to a so here this set, or more precisely, it's really a groupoid. Each element has a automorphism group. Where when we do counting, we have to put the size of automorphism group into consideration. So here, so this is going to be replaced by so in the Hermitian case, it's the unitary Shimura variety. So here, of sign signature. So we may think of this as one sort of one counterpart in the indefinite case. So earlier I considered positive definite lattices. Here I have to look at a indefinite Hermitian space. So I'm going to look at this modular scheme called MN. So I'm going to be very sketchy here. So this is a modular stack which parameterize pairs of abelian scheme with a action by. Now I'm going to the global situation here. So now globally, so I have my f over f0 being a, well, let's say, and we have the case when the base field is Q. I have a quadratic imaginary field extension. Same field extension. Then I look at a principally polarized abelian scheme with a OF action with a complex multiplication by the row of integers over the quadratic field, and also elliptic curve with the same with the same kind of data, complex multiplication. So here the dimension of A is n. Dimension of A0 is 1. So both have OF action. And the principally polarized. So basically, there's no interaction between those two pieces of data. And I also impose the sign condition, sign n minus 1 to 1, when you consider the OF action on the Lie algebra of the two abelian scheme. So the complex points, just to give you some idea what it looks like. So the complex points looks like a disjoint union of finite disjoint union of some quotient by discrete subgroup acting on a unitary group of size of indefinite divided by its maximal compact. So it's some Shimura varieties attached to the unitary group. So this is what, if you replace the signature by by a totally definite, you will actually end up with a group point which rediscover this set. In that sense, it's really a generalization to of that set we used before. But now it has more kind of interesting geometry because it has a positive dimension, right? Complex points can be described using the involving isometric group of the Hermitian form. And what's even better is this. This is the Riemann for stack over spec of F. Let's ignore the bad fibers, so there'll be issue with this prime above, primes P which are ramified, but anyway, let's consider maybe the inverting some bad primes. So some bad primes being inverted. And then I have a smooth the Riemann for stack over the integers of dimension, relative dimension n minus 1. So what's even nicer is that you can define a lot of, I can define an analog of a theta function. So here I define a theta function here. I can actually now define a theta function where I have to rewrite this counting, this was counting the number of, remember here, this n lambda of m was really counting the set of vectors x inside lambda, whose norm is given by this given integer. So I can sort of make an analog. So now there is a divisor defined by using the modular definition, modular space I just defined. So Kudla-Rapoport we defined. In some sense, analog of this, so this is viewed as a subset. Lattice n. So here the defined divisors, namely codimension 1 objects. Let's call it Z of M. So this will be it's a functor parameterized. Again, the pair of a point on this modular scheme I defined. But with one additional piece of data, just like here, I have to impose a vector here. So here I have to impose one homomorphism from the abelian scheme elliptic curve A0 to the abelian scheme A, which is a homomorphism between abelian varieties. And what's nice is I have polarization for both, so I can actually measure the size of this homomorphism. Namely, I can define a Hermitian norm on the space of all such homomorphisms using polarizations. And you end up with a number. So that number is prescribed by this integer. And since the polarization is principal, so this is actually, since those are polarizations, so you actually get a positive definite Hermitian form on the space of all such homomorphisms. I'm going to impose this condition. So that is sort of the analog of this set of vectors with given norm. And so generically, this has codimension 1. So there is a natural map going over there. So this has codimension 1. So therefore, I can define the same. Well, I can also put this. So I can define given. I can form intersection product, which is I can form given T, which is a n by n Hermitian, or actually arbitrary number, say R times R Hermitian. So I can consider intersection of Zm1. So let me do it this way. Let's define Z of T. So same kind of definition, except I have to impose not just one homomorphism between abelian varieties. I have to impose, so how much depends on the rank, so that pairwise parent under the Hermitian form is the, well, say Tij. Yeah. So in the codimension 1 case, everything is very nice. But if you have so the higher rank matrix here, the naive definition might behave terribly. For example, the dimension might not be as expected. It might have larger dimension than what you want. So the sort of the correct way of defining is to defining this sort of. I mean, one should consider maybe the sort of the derived structure inside. So using intersection theory, this means I can form a class in the child group. So I can, so yeah, I should have, one should have done is to consider Zm1, what if T, let's say T has diagonal elements M1, Mi, Mr, with off diagonal, we don't care. So we should have defined Z of T using, well, it's a class represented by the sort of the derived tensor of the structure sheaf. So M1, M2, and so on. So this will give rise to a class of correct dimension supported on the naive definition. So that was a naive definition. So here I can refine the definition to get a class of correct codimension. So codimension R. So in the case of maximal, so if I consider n divisors, so now if T has rank n, so this will, in this case, actually, what I can prove is, in fact, Z of T is actually proper. It's a proper scheme, I mean, stack. Therefore, I actually have some zero cycle. I mean, R is, in this case, I have, let me actually give let's define this as, put a hat here. So I remember the derived structure here. So this actually is a class codimension n. Well, not code, sorry. I should have written support. Okay. So anyway, I can get a 0 cycle on with the support 0 of t. Well, let's write it this way. So actually get a class 0 cycle 0 of t. So I can take a degree, which is actually an integer. Well, we can stack, so I have to take rational numbers. So that is the analog of Kantian, sort of Kantian vectors with pairwise parent being equal to t. So this sort of is replacing what I erased, this left-hand side. So the theorem one can state is theorem. So I'm stating for Hermitian space, but we also have a version for quadratic space. So this is joint with Chao-Li. So we prove the degree of this cycle is 0 t. So suppose t is positive definite, rank n. So then this is equal to a derivative of the local density, the product of the local density. So, okay, I'm writing as t, although locally for each t, I have a unique, up to isometry, a unique integral Hermitian form. Then put q of negative s, so or p, so prime p. So if I normalize correctly, so another way of stating this is if I form a theta function. So I should have so I can form a theta function, or arithmetic theta function, which is degree of 0 t, q to the t. Well, okay, this q is not the same q, unfortunately. So here q was the cardinality of a residue field. So I should have places v, so qv. So, density at v. So here it's the q parameter defining the Fourier coefficient of the Siegel module form. So t. So what this is stating is that this is related to Siegel Eisenstein series. So Eisenstein series. How s for so the Siegel Eisenstein series for Hermitian form. So of course, the reason I didn't write in this way is because, well, I only told you how to define this when t is positive definite. We're supposed to have more terms than just positive definite terms in this sort of formulation. Yeah, this is also because, well, again, t is rank n. Well, t is positive definite. So the reason. Times log, right, divided by times log of suitable q, qv distinguish v. So what happened is this, this proper scheme actually lies purely at one spatial fiber. So that's a unique prime, so that this scheme actually, so it's sort of its image to the base run. It's actually has only one prime number. I mean, it's only Right, so actually there's a unique prime of OF, so the image is only one prime. So, called a V, let's place a V. So that's what happens over there. So this rational number times a log of QV give you QV0, V0. So therefore, so it's rational number times a log of some prime Q. So that's the key result. So when compared with the earlier formula I wrote, it's sort of the interpolation of the first derivative of the local density. So I will end up with application of this equality. So this application is due to right here. So application is due to Charlie and Yifeng Liu. Where they prove, well, using this using Raleigh's inner product formulation, so we can prove so for this Shimura variety I wrote, so if I take a automorphic representation, Caspidal automorphic tempered representation of the group involved over there, then if the L function of this representation base change to F has order 1, so if the first derivative doesn't vanish, which means the order is 1, order vanishing is 1 in the center, then the child group of this modular scheme, the pi part, well, you can define by localizing as a Heck module at the maximum prime corresponding to this representation. So this is non-zero. So there's sort of the lower bound for the child group. So the existence of non-trivial elements in the child group. So intuitively, one can think of relating both sides to the local density. On one hand, those cycles I wrote, those divisors or their intersections are related by local density through this formula. On the other hand, we knew local density were connected by Eisenstein series, and Eisenstein series, by Raleigh's work, is known to connect to the L functions. So since I have finished 1/3 of my prepared, so I think I'm happy to stop here.
See how we're going to do it.
N equal to 1.
Repeat the question.
Oh, so the question was what happened when n equal to 1? Well, n equal to 1, right, okay, so, here I have, I should have said n is even, well, okay, n is even, at least 2 for this application. For that formula, it's for all n, so n equal to 1, yes, yeah. Right, yes, you have a relative dimension 0, yes. For this scheme, yes. That's right, yes. So in that case, it's still sort of, and it's funny, you have to distinguish positive definite and negative definite. So in this case, I have a negative definite case, where before I had a positive definite case. So it's actually, there are different cases. So the signature matters. Although the groups don't make difference because the groups seem to be the same locally at least at infinity.
I have a question.
Yeah.
In Siegel and Wei, they both make the big point that, say, Siegel's first proof of the mass formula, he had to assume the Hasse principle.
Right.
Of a number field, he has to assume Hasse's work, and then he proves the mass formula. And they both make the point that when they give the proof modular forms of the mass formula, that they don't have to assume it, they deduce the Hasse. So how does that impact in what you're doing, where you're proving it using this something's an Eisenstein.
That's a very good question. So Peter's question, what did Hasse principle for Hermitian form or quadratic form show up anywhere? So indeed, they showed up here. Actually, I should have separated according to the Hermitian spaces here. So actually, this space will be disjoint union of Shimura variety attached to different Hermitian spaces. I should have distinguished. I should have separated them. So my result really applies to. You should have prescribed one. So it doesn't. In other words, so the theorem is when I define Eisenstein series, I should have specified one Hermitian space to start with. I'm not even mixing different Hermitian spaces together. So the result should be really starting from a Hermitian space. Then I define this space. Then I also define Eisenstein series. Then my equalities between those two quantities defined starting from the same Hermitian space.
How far away is this guy from being like some kind of?
So no, it's very complicated. So here I wrote its dimension could be as large as half dimension, but it's always in the supersingular locus. So it's as complicated as a supersingular locus of this modular scheme. So for example, it might have some irreducible components which look like some Dolinostic varieties. In the case of three dimension, so if n is 3, you might have a Fermat curve of degree q plus 1 if q is the prime, So that's something like x to the q plus 1 plus y to the q plus 1 z to the q plus y equal to 0. So this is a curve, projective curve. So that shows up as one irreducible component of the underlying scheme. It has incorrect dimension because you would hope to have 0 dimension, but that's kind of positive dimension. There's no simple description. What happens is actually sort of this derived definition of this class actually behaves much better. In other words, you would hope to collect with the local density or Eisenstein series. So the question is there any philosophical reason why we get a derivative rather than special value, right? One answer, I don't have a very. So one answer is that I'm intersecting something over a variety over spec of integers. So typically, if you take intersection number of a family of objects over parameters by spec of integers, you expect to get some first derivative. Right, so here this application indeed as an intermediate process is to relate say this type of a cycle, but for t of half of n, rank being half of n. So you have some middle dimensional cycles. So what I'm computing here is really the intersection number between two such cycles, and by the conjecture of high dimensional BSD, we're in like Valence and Bloch type conjecture we mentioned 2 days ago, where we're expecting to have a sort of rank 1. We only construct one cycle, right? So one, essentially one, but using Heck correspondence you get more, but essentially just one object, one spatial cycle. So, but I think actually the reason is because I only have I have a family of objects which varies over one sort of over spec of Z or OF. If you have kind of genuine family over spec O times spec O, you would expect to have second derivative, like the case in the function field over function fields. So here I only have kind of objects which only varies in one direction in some sense.
Anybody on Zoom have a question? No? No, I think after 3 very impressive lectures,
Thank you.
we have to thank you for a fantastic visit. Leaving, he's got an Uber coming in an hour and a half, so anybody who wants to quiz him for another hour, you can call him now. But others who don't want to quiz him, I've been asked to invite you to a party on PL. We have a party upstairs, and everybody who's in the audience. Let's thank Wei Zhang for
Thank you.